So, in the previous class, we had first discussed, we have presented this outline of this course. Okay, a detailed outline was given as to what all will be covered, and then I tried to develop the motivation for this theory of probability, okay, in very general terms. And that time I mentioned that this theory will be developed using some solid mathematical foundation of set theory, classical set theory. Okay. And then I discussed the basic set theoretic notions, definitions and operations at length. Today, I will be using those concepts of set theory to first introduce you to the topic of to the subject of probability space, and we will be discussing the properties of probability space, and using this definition and properties, I will then go into what is called axiomatic definition of probability. We will enlist certain axioms, and then we will get into the consequences of those axioms, and then I will try to relate them to real life world, because after all the axioms are purely mathematical. Okay. And then once those axioms are given or described, then I will get into some further sophistications in the form of something called field of sets. In fact, a particular class of fields, particular type of field called Borel field, and in this Borel fields only mathematically we can apply these set theoretic these probabilistic axioms correctly. Okay. So, I will go up to that. We will also consider some examples. So, first I start with probability space. First, let there be a set S. This set can be finite, countable or infinite. Finite and countable are the most, the simplest of all cases. Finite, the total number of entries is finite and countable. It can be infinite but countable. Like, I mean, do you know, can you give an example of such set where the set is infinite but countable? Say set of integers is countable, is called countably infinite, or set can be itself non-countably infinite, for a real line. Okay, it can be anything, but for our treatment, I will try to first take those examples where S is finite and countable. Okay, and then we will try to when you try to generalize it to those infinite sets, then only I have to get into that what I said, field of sets and Borel field and all that. Okay, so this set S, it consists of experimental outcomes. I will explain. Meaning S is something like E1, E2 dot 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 dot. The way I am writing, it's giving an impression that it is countable, but it may not be. Okay. Each of these elements E1, E2, each is an experimental outcome. Like that means some experiment is going on or some observation is being made. Either you observe E1, something, or you observe E2, and likewise. Collection of those basic experimental outcomes, all possible outcomes I would say. You collect all of them, that is this set S. Okay. Then comes event. An event is any subset of S, which means E1 itself could be an event, because E1, a set consisting of E1 only, there is only an experimental outcome E1, could be a subset of S, which means that is an event. E2 itself is an event, and likewise. Then an empty set phi, that is also an element of S, that also is an event. What it means and all that we will see later. And not only that, you can now have things like this, for instance, say EJ dot 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 dot, some combination that is an event. This event means actually that either observation was EI or could be EJ or could be something else. Okay. For instance, suppose you are tossing a die, say. Okay. So, there are 6 faces. So, actually there would have been 6 elements here, 1, 2, 3, 4, 5, 6, whichever comes on top actually. But you can now look for those cases where only even valued face comes up. Okay. So, 2, 4, 6, that could be one event. It does not mean that all 3 will come simultaneously, that is not happening, isn't it? But either this or another one, just their collection, that it denotes an event. In that case, the event means that die is showing up as even. Okay, only the even faces, even numbered faces are showing up on top. Okay, that is an event. So, that way subsets of these constitute event. But here one thing I tell you, I am not making the statement that you should include all possible subsets. I am rather silent here. Subsets of these constitute event. Sometimes all possible subsets are okay, sometimes not okay. In fact, when you come to this infinite set, when it is infinite set, all possible subsets are not allowed. They do not constitute legal, I would say, in our terms, or valid events. Okay, it is there that concept of Borel field will come to define what could constitute an event and what not. Okay. So, this is an event. Okay. Then I would say that S itself, which is the probability space, this S itself is an event, but it is a certain event. It is an event after all, because what is an event? It is a collection of, it is a subset, that is a collection of all those experimental outcomes. Okay. Now, a collection where all the outcomes are included, that also is a collection, but that is nothing but S. So, that is an event, but that has to be a certain event, because one of the outcome has to take place, there is no other possibility. So, S is called the certain event okay, and phi you should always write like this. Phi alone is not the set, it is a set with phi being the element, which is in fact null set. This corresponds to an impossible event. Okay. Now, some more definitions or and discussions also. Suppose there is one particular outcome, EI, that is the outcome. It is a part of, it is an element of event A. Event A is what? It is some collection of those experimental outcomes. EI is one of those outcomes, it is part of event A. And now, when you conduct the experiment, suppose outcome turns out to be EI only, now this particular outcome, then we will say that event A has taken place, because event A could have contained EI or maybe EJ, maybe something else, EL, EM, one of them has taken place means event A has taken place. That also means that whenever you conduct the experiment, certain event always takes place, the certain event that always takes place, because any outcome, after all there has to be some outcome, but any outcome is an element of the certain event S. Okay. So, that always takes place, certain event always takes place. Okay. Then suppose I have got one event A, element of subset of S, another event A B, sorry, again subset of S. Okay. Then A plus B, in our notation plus actually stands for union, but instead of using that U sign I discussed in the previous class, since I want to go along with this book, I use the plus sign, which is more like OR. Okay. So, A plus B, this also constitutes an event. What event it constitutes? That either the outcomes contained in A, they take place, or contained in B, they take place. There could be overlap between A and B. Okay, there could be some experimental outcomes which are both part of A and part of B, but some could be exclusively for A, some could be exclusively for B. A plus B means either A takes place or B, one of them has to take place at least. Okay. So, this is a bigger event in fact. If B and A both are non-empty, then A plus B actually corresponds to a bigger event, because it has more number of outcomes in general. In general, of course, B could be a subset of A. So, A plus B is A itself, but in general this is a bigger event than either A or B. All right. So, that means I can also write both. Both means the overlap or both occurs. Okay. On the other hand, consider A B. This is actually A intersection B, but again going by the notation of the book, we reserve this product sign as if it is A and B. Okay. A B also is an event, but it means that both A and B must occur. Okay. That means, suppose if I consider the Venn diagram, this is A and suppose this is your B. Okay. If both A and B have to occur, that means outcomes should consist of experimental outcomes that lie here. That is where A and B intersect, isn't it? Then only both A and B can take place simultaneously. Okay. If A and B are such that they are mutually exclusive, that is, if A B is nothing but this, that means there is no overlap between the two. In that case, the events A and B cannot take place simultaneously. If A takes place, B cannot, and if B takes place, A cannot. For instance, when you just take the set S, you have got E1, E2, those are the basic outcomes. If you just take E1, a set with E1 only or a set with E2 only, they are mutually exclusive, because either E1 has to take place or E2, both cannot exist simultaneously, both cannot take place simultaneously, right. Okay. All right. Okay, let me okay. So, I now get into the axioms. Axioms of probability. Actually, let me tell you something about what is meant by an axiomatic treatment. Often, you know, in physics or engineering, we have some physical concepts, okay, and we try to associate some kind of calculation, some kind of, some I would say rough mathematics with that. But when mathematicians step in, they look into the mathematical aspects of the variables present and all that. They don't go into the physical part so easily. they try to find out the basic mathematical properties that those variables or the existing mathematical structure must satisfy, those basic minimum number of properties that they satisfy, and then based on that develop a theory. Those basic properties are called actually axioms. Okay. Like idea of probability was existing earlier also, but when mathematicians stepped in, they tried to find out, okay, if there is something called probability in practice, like the other day I told you something about what we say frequency based interpretation, that if suppose capital N number of trials are taken and only n small n number of outcomes of a particular kind take place, then approximately small n by n is a is a chance of occurrence, which we call probability of that event. So, with those kind of definitions, ad hoc definitions already present, when mathematicians looked into them, they found out that they should satisfy some basic properties, those probabilities, okay. And using this you can develop further, you can establish other properties with which also people in science or engineering familiar, okay. But then now you are forming a solid foundation. Those basic properties are called axioms. Here we are saying that with every event we assign a value, and that value we just term probability. What is its physical meaning and all, we are not bothered at the moment. Okay. So, if that is for each event A we assign a real value P A called probability of the event A. So, what we are doing? We are just looking at all possible events that are available, and to each I am assigning some value. Value is real, not complex. Again, it is abstract. I am not at the moment bothered by what is the physical significance of those values and all that. I am only bothered about the properties that this value should satisfy, basic mathematical properties which you cannot beat. If you violate those properties, the whole thing crashes. Okay. So, those values are called probabilities. I denote like this: P of A is the probability of A. It should satisfy some properties. These properties are properties. Number 1, P A, any probability that I assign, any probability value, that must be non-negative. It should be greater than or equal to 0. Okay. Then probability of the total event, that is the certain event, that must be 1. Okay. See, will not be imposing so many conditions, so many properties. That is the beauty here. Some just 3 basic properties will be taken up, and many other properties with which we are familiar, they will follow from this. This is the beauty here. The mathematicians find out what are the basic minimum conditions that are required to be satisfied by this measure P of A. Actually, this value P of A is sometimes called measure, probability measure. There is an established topic called measure theory in mathematics, which is intimately connected to probability theory, but I will not get into that. It is called probability measure. What are the basic properties, minimum basic properties that this should satisfy? These 2. And the third one is, if A is an event of S, B another event, and they are mutually exclusive, that is A, B is phi mutually exclusive, then P A plus B. What is A plus B? That is, firstly A and B, they are mutually exclusive. So, A consists of some experimental outcomes, B consists of some other outcomes, there is no overlap because they are mutually exclusive. And now P A plus B means you now consider the bigger event where outcomes of both A and B are present. Any one occurring will be enough. We can say that event A plus B has taken place. Probability of that bigger event should be equal to P of A plus P of B. That is all. Okay. Now, let us see what consequences follow from this. Okay. Let me call it those three things. Actually, instead of calling them properties, I mean it's better to call them axioms. Okay. And I call it properties here actually, properties or consequences. First, if you consider the empty set, that is the impossible event, because no outcome. Empty set means there is no outcome. That means however much you try the experiment again, you cannot get that thing. That is the impossible event. So, if A is phi, then P A equal to 0. How it happens? I will just use those three axioms only. Okay. Now, you see, take any event B, element of S, and B is not this. That is, I take any non-empty subset, and subset which actually is given to be an event, a valid event, call it B. Then obviously, B and A, what is the intersection? Phi only. A is phi, empty set, and B is any non-empty subset. So, their intersection is phi. In that case, that means P of B plus A, that is B union A, will be, right, but B union A is B only, because A is empty set. So, that means P B, and we have P B here, plus P A, which means P A equal to 0. Okay. So, the impossible event has probability 0, total event has probability 1. Okay. I will also show that as the set expands from smaller event, as you get into bigger and bigger event, probability value increases. So, that when you go to the final biggest event, which is the total event is, then it finally gets the value 1. So, this is how we go close to practice, because that is what happens in practice, is it? But you see, we have only those three axioms, only those three are necessary to develop the entire concept with which we are familiar. This is one consequence. Okay. The number 2, since A plus A bar is the complement of A union A bar, that is equal to total set S, and A bar, they are mutually exclusive, that means their intersection is phi. That means P of A plus A bar, since both are mutually exclusive, I can write using one of the axioms, axiom number 3, this thing, all right. But A union A bar is nothing but total set S, and P of S going by exponent number 2 is 1, isn't it, which means P of A bar is 1 minus P A. So, when event takes place with some probability P, then the probability for the event not to take place is 1 minus P, all right. Now, suppose A and B are two subsets, two events which are not mutually exclusive. So, I cannot write P of A plus B is P of A plus P of B, then what can I write? That is the question. There is now I have something like this, property 3 actually. We have got something like this. This is A, this is B, this area is your AB, okay. Total is A plus B, all right. So, here A and B are not mutually exclusive, that is given A, B, it is not, this is given. In that case, question is what is P A plus B equal to what? This is a question. So, this is one formula we have to derive. First, let us see one thing, it can be derived in various ways. Consider A plus B, that is this entire set, isn't it? Can I write it? I want to write it as the union of two disjoint subsets. Disjoint means their intersection should be phi. So, one possibility is this, take this side as 1 and rest as it is. Are you following me? That is, take A as it is and do not take entire B, but take only this part of B. Okay. That is this side, this side. That means A plus B can be written as A union this side. Now, what is this side? Firstly, using this Venn diagram, things can be written very easily. This is A. So, outside A is A bar, isn't it? Outside A is A bar. This entire thing, all these places, this is A bar, including this. This entire thing is A, outside this is whatever you have, that is A bar. That A bar consists of these open spaces plus this space, all right. With that A bar, if you take intersection with B, actually if you have the intersection between A bar and B, what do you have? B is this entire thing, but out of that this part falls under A. So, that does not come under intersection, this part falls purely under A bar, because A bar means outside this area, isn't it. So, this part is nothing but yeah, and they are mutually exclusive, all right. That means I can write by axiom number 3 now, P A plus okay, and then this fellow is coming, this is a problem. A bar B is this area. Now, consider B. B has got two parts. One is this part, which is A B, another is B bar, another is this part, A bar B, right. I from this is followed. Similarly, consider B now, you call 1. Consider B now. What is B? B is this entire thing, it has got two parts. Say I want whatever parts I have, I want them to be mutually exclusive, because axiom number 3 works only for mutually exclusive subsets, isn't it? So, I break B into two mutually exclusive parts, one is this and is this. This part is, we already know, A bar B, and what is this part? A B. A intersection with B, isn't it? So, you have got A B plus A bar B. As a matter of fact, if you know apply OR logic and all that, B can be common and A plus A bar is 1 that way, but let us follow this Venn diagram thing, let us not bring logic variable things here. This is your B. That means PB is equal to what? These two are mutually exclusive, isn't it? This and this. That means I can apply axiom 3 again, but then it becomes PAB plus okay. So, this value I take from here. What is P A bar B? That is P B minus this, and that I replace here, and that gives me the formula. In this case, P A plus B P A plus, you will get this. This is the result. Okay. Finally, this was property number 2 or 3. So, another thing we see, number 4. Suppose I have an event B, that is a smaller event, there is a bigger event A, that the event is growing. From B I get into say A. Both B and A are events, they are part of S, subset of S, but B is contained in A. Then we will show probability for B is less than the probability of A. How to show that? Once again, using Venn diagram, if you take the Venn diagram, this is your A and this is your say B, B contained in A. So, A can be written as, I again want to write A as a sum of two disjoint subsets, one is B, another is outside portion of B, some that part which lies outside B, but inside A. That will be what? Firstly, take B. What is B bar? B bar means entire zone outside except for the area given by B, the entire area outside that, that is B bar. If you take intersection between that and A, then you will get what? After all, intersection between A and that, so all areas of A have to be included, but not this, because this is not part of B bar. So, only this part will be. Okay. So, that means you can write A as B plus A B bar, okay, and these two are disjoint, which means P A is by axiom 3 P B plus, and since both are non-zero, this is clearly greater than or equal to P B. If this is empty set, then only these two are same. When can this be empty set? when B is B itself is A, there is nothing, no area here. Okay, then only P A and P B can be same, but as long as there is some non-empty subset in the form of A B prime, probability of the smaller event B becomes less than the probability of the bigger event A. Okay. Now, this has been done axiomatically. I have not related to real life examples, but let us consider those frequency interpretation cases and see that these axioms and the consequent properties, they satisfy those physical things, physical observations. Okay. Suppose we are conducting an experiment out of which, say I am saying that frequency interpretation, I am coming to this. Suppose we are conducting an experiment, we have taken a very large number of trials, say capital N, large number of trials, out of which one particular event A occurs N A times. Okay. Then classically we know the approximate value of the chance of occurrence of A is what? N A by N. Okay. That is the physical probability actually with which we are familiar. Okay. Physically that is, for us, that is probability, provided capital N is large. But you see that satisfies these properties. Firstly, P prime A, see I am using a prime here, it is because P of A was used for giving the axiomatic definition of the probability of A, event A, whereas P prime A relates to the probability with which we are familiar, that is based on frequency interpretation. Okay. So, this P prime A is nothing but, as we know N A by N, but this is always a non-negative number, isn't it? Minimum value could be 0, that is you try capital N number of times and out of this time N number of observations also you do not get the event ever. So, in that case N A is 0 and minimum value is 0, but you cannot get it negative, right. So, this satisfies axiom number 1. Then axiom number 2 is what? That probability of the total event is 1. Now, you see out of capital N number of trials, on N A occasion you get event A, on N B occasions you get event B, and so on and so forth. Okay. But total event means say event A, okay, then event B, event C, dot 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 dot, but total, this total thing should be equal to S, isn't it? What is the probability of S? Out of capital N number of trials, how many times I get the total thing? N A times here, N B times here, N C times here and all that. So, total is N A plus N B plus N C dot 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 dot, that by capital N, isn't it? That is by capital N, but this is equal to capital N itself. After all, when you try capital N number of times, on certain occasions you get A, certain occasions you get B, certain occasions you get C and all that. Okay. But if you add all of them, then that equals N, isn't it? And capital N is large, so that it's so large that all the events really take place adequately. A also has taken place on sufficient number of occasions, N A occasions, B also has taken place, C also has taken place and all that. Only thing is, if you add up N A, N B, N C and all that, you get capital N. Okay. So, so since capital N is large, you can take that entire happening, that okay, N A times capital A, N B times B and all that, that entire thing amounts to observing the total set. Okay. So, in that case the probability will be 1, because number of occasions on which you get the total thing is after all n a plus n b plus n c plus dot 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 dot, which is n divided by n, which is equal to 1. Actually, it is trivial. Axiom 1 and axiom 2, they are satisfied trivially. And axiom 3, suppose out of capital N number of trials, n a occasions you get on n a occasions you get A, n b occasions you get B. A is an event, B is an event, and suppose they are mutually exclusive. That is, event A may involve some outcomes, either this outcome or that outcome or that outcome, like that. Same for B, but there is no overlap. In that case, if you try capital N number of times and on any occasions A occurs, any B occasions B occurs, you are assured that on each of the n occasions where A is occurring, B is not occurring, because they are mutually exclusive, isn't it? There is nothing common, no common outcome between the two. Okay. In that case, if I now look for the bigger event A plus B, if I now look for the bigger event A plus B, that means all outcomes of A or all outcomes of B, any of them occurring, what will be the probability? Out of capital N number of trials, n a times you are getting outcomes from A, n b times outcome from B, and no overlap. So, n a plus n b times you are getting outcomes of A plus B, isn't it? That means P prime A plus B will be what? No, not 1, n a plus n b by n. Try to understand this. A and B are mutually exclusive. A occurs n a times. In each of these occurrences, B does not occur. There is nothing common. And same for B. B occurs n b times, and each of these occurrences A cannot occur. Okay. So, on n a plus n b occasions, what do you get clearly? Nothing less than this. That is what I am saying. It has to be n a plus n b. On n a plus n b occasions, what do you get? We get either events from A, either A or B. There is either some outcome from A or some outcome from B. Okay. Nothing less than n a plus n b, because they are mutually exclusive. Okay. So, what is the probability? That divided by n, and now that you write as n a by n plus n b I by n, which is nothing but P prime A plus P prime B. All right. So, those axioms really satisfy the physical facts. Okay. Then another definition. Suppose two events are given A and B. We would say that they are equal. As per one definition, they are equal if the outcomes contained in A, they are same as those contained in B. This is a very strong definition of equality of events, that they are identical. But in probability theory, many things are presented using the notion of probability. I would say, I would give an alternate definition also, that says that two events A and B, they are equal if you consider this. You consider the Venn diagram first. Okay, this is your AB. If the probability of either this event or this event taking place is 0. Now, probability of an event is 0 if it is an empty set. So, indirectly it means this half and this half, they are empty, that means they overlap entirely, which means A and B are identical, but you see there is a mathematical difference. Physically it appears to be so, but in terms of conditions there is a difference actually. I am not saying they are equal, I am using those axioms, using that I am presenting the equality of set two events in this way, that probability of this event, what event? What is this portion? This part and this part. This is actually A plus B. What is A plus B? This total thing is A plus B, an intersection of this. AB is this, its complement is the entire area except for this, that when intersects with this A plus B, only this half goes, this portion goes, both this and this remains. This using this De Morgan's law and all that, you can even write as this actually exclusive OR. And they are mutually disjoint. We would say that A and B, these two events are equal if probability of this is 0, which means this is an empty set. The difference is that, you see, again it is purely using mathematics, I mean, what mathematicians say. I said if the set is empty, then the P of empty set is 0, that we proved using those axioms, but I have not proved that if probability of a set is 0, the set is an empty set, isn't it? There we are silent. Okay, we are not. I can also say that you are not trying to force some strong condition there. Okay, we are silent there. That is what we have in this definition. In one definition, we are very strong. There is a strong condition that two events are equal if they are identical. They have the same elements and all that. All right. But in the other case, I am putting it in an indirect way, that probability of this portion, this event union with this event, which are mutually exclusive, that should be 0. Okay. Which means if indeed it is that probability of an event 0 means the event is impossible event, then obviously that would have meant this part and this part are empty sets. A and B, they overlap entirely here. Okay. But it is more general than that. You follow the distinction, right? Okay. Now, for this to happen, that is if the probability of this is 0, then this is satisfied, that is P of this part A B bar plus A bar B, this is equal to 0 if and only if P A equal to P B equal to P A B. Now, if this is satisfied, this will be satisfied, that I will show, but if this is given, then show that this is true, that I leave as an exercise. But I need this Venn diagram, so maybe I have to draw again, or before since I do not want to draw it again, let me tell you before what I want to do. A I will write as this part, which is what? A B bar, A B bar, isn't it? This is A B bar, as I told you, the entire plane except for this B. Intersection between that and A will be only this, not this part. So, A can be written as sum of this, that is A B bar and A B. Okay, I will use that. That is A is logically it is very obvious. You can take A common and B or B bar is 1 and all that. Okay. That means these two are mutually exclusive. So, I apply that axiom. Okay. But this is given to be this P A equal to P B equal to P A B. I am assuming that is given, that means these and these are same, which means P A B bar equal to 0. In a similar way, I can show that P A bar B equal to 0. This time I took A, next time I will put it B, okay, replace A by B and B by A, like that, which means I had to prove this, no, but these two are mutually exclusive. A B bar one half, A bar B another half, which is same as this is equal to 0, but both are 0. So, given that condition that P A equal to P B equal to P A B, okay, you prove this, you obtain this, but I will leave it as an exercise for you to show that given this, show that it amounts to P A equal to P B equal to P A B. Okay. Now, I get into fields of sets. Firstly, fields of sets. Actually, I said that given any probability space S, what is an event? Event is some subset of those outcomes, but that time I said that it is not that all subsets will qualify for events. As far as a finite countable set is concerned, there is no problem, but problem comes in infinitely long sets, sets which are infinite, okay, their problems can come up. Okay, not all subsets qualify for events. This is a mathematical problem, I will not get into that. I mean, it can be shown that if you consider all possible subsets of an infinite set and consider the subsets to be events, the axioms do not work perfectly on all subsets. That is why I have to use now another concept called fields, that is something called Borel field. But before I get into Borel field, I quickly just define the some basic axioms of the fields. A field F is a non-empty class. Actually, when you define set, we say it's a set is a collection of objects and all that, but when you have a collection of sets, then we use the terminology class. So, it is a non-empty class of sets, it is non-empty. So, F may consist of empty set, but that is not alone, it will consist of some other sets also. Sets, it should satisfy two properties, that is, so that number 1, if A is part of F, then complement of this also must exist in the field. Okay, this one requirement. If A is part of F, A complement also should be part of F. A may be taken from that event, from the probability space S, from there I took A, but then I know what is the A complement there. Now, I am constructing a field. If A is present in that field, A bar also must be present. And number 2 is, if this should be actually element, because these are now sets are now elements of the class. Class is what? A collection of sets. So, each set is an element of the class, so it should be element, not subset. Okay. If then these two, using this we will show that this applies also to the intersection. Using these two we will develop some properties, we will show that if A is an element of F and B is an element of F, then A B also is an element of F. So, the next class I take from here, okay, and I get into something called Borel field, and there I give the more exact definitions actually. Okay, Borel field, I will tell you why Borel fields are required. Okay, because when you have got that infinite set, all subsets do not qualify for events, only those which give rise to Borel fields they qualify for events. Okay. After having done that, I will get into again more practical things, there is a conditional probability and all that, we will solve some problems also. Okay. So, that is all for today. Thank you. Okay, so in the last class we discussed the axioms of probability, okay, their properties, and then we discussed something called field of sets, okay, and in that connection we mentioned Borel set, Borel field. Okay. I will just touch upon those things today to start with, and also explain the motivation for considering these, but this is again only for mathematical correctness, but having just done that, I will move on to the notion of conditional probability. Okay. That I will be explaining first notionally and through examples, then using this conditional probability I will find out its properties, then we will discuss something called total probability and Bayes theorem, again we will take up some examples, and then we will go for statistical independence of two events, and we will of course try to give physical interpretation of these. Okay. So, as I mentioned in the last class, I will consider a field, of sets F. It will consist of suppose sets S1, S2 and dot 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 so on and so forth. Okay. Now, this will be a field if for any Si, I would say element, because it is a field means it is a class of sets. So, each set is an element of this class. Okay. If we should have Si bar also member of F. That is, if a set belongs to this field, then its complement also must belong to the field, number 1. And number 2 is if A is an element of F and B is an element of F, then their union also is an element of F. These two conditions must be satisfied. There are some properties which follow this, which we will be now considering. Sorry. Okay.